Hello, everyone. My name is Joshua Zhao, and I'll be presenting the paper LOKI, Large-Scale Data Reconstruction Attack Against Federated Learning Through Model Manipulation. This work was done with my collaborators at Purdue University and University of Southern California. I'll first begin by introducing federated learning. So federated learning was proposed by Google in 2016 with the main goal of allowing machine learning training while still maintaining the privacy of user data. And this is done through a decentralized approach. Essentially, data does not have to be sent to a server for machine learning to be done. Rather, a server can send a machine learning model over to the clients instead. And you can think of these clients as a cell phone, for instance. Here, a cell phone would then train the machine learning model with their local training data, which is private, and then send the machine learning update back to the server. Essentially, the client training data can stay local while machine learning can still be done. Now, despite this, user data can still be leaked from these updates being either the gradients or the final model state. I'll give a quick introduction on Fed average and secure aggregation. Both of these methods make attacks more difficult. So Fed average, while not designed to be a defense, makes attacks more difficult because clients perform several local training iterations before sending a final model to the server. What this means is that any intermediate steps that the model has taken are unknown to the server. And with these more unknowns, attacking these updates becomes much harder. Secure aggregation, on the other hand, is a method primarily aimed for defense. What it ensures is that a server can only see the final aggregate model. Individual updates are cryptographically encrypted such that the server, if looking at the individual updates, cannot get any information. However, after aggregation, the server can then see a decrypted update, an unencrypted update. Now, this is very difficult because in the context of secure aggregation, there can be hundreds of clients. Think if there's a batch size of 64 and 100 clients, that would be a total of 6,400 images contributing to just the single final update. Now, if we want to leak images when there are this many images, this large scale really makes it so that attacks can only leak either a few samples or just outright fail altogether. Our attack LOKI falls under the class of attacks called linear layer leakage. And these attacks operate under an idea that a fully connected layer can be used to leak images through the gradients of the layer. For instance, if you look at the figure to the bottom right, you can see the dog image highlighted in orange activates a single neuron. When we do the division of the weight gradient and the bias gradient of that neuron, we get the reconstruction. If you look at the two images below, highlighted in blue, on the other hand, they activate a different neuron, but they activate the same neuron instead. Now, when reconstruction is done, the reconstructed image is a combination of both. In linear layer leakage, we would call this a failed reconstruction. This is the fundamental problem that linear layer leakage methods try to improve on. Robbing the Fed is a method which proposed a very efficient approach for leakage. Essentially, they would have the weights of a fully connected layer measuring some aspect of the image. You can think of this as, for instance, the average pixel brightness. Now, in a data set such as CFAR 10, for instance, the average pixel brightness may follow some sort of distribution, and for instance, a normal or a Gaussian distribution. Now, the biases of the fully connected layer can then follow this distribution, essentially acting as a cutoff for activation. So as an example, let's consider an image and let's say they have an average pixel brightness of 0.5. If the bias is below that cutoff, for instance, let's say it's negative 0.4, negative 0.3, or so on, the image will activate all of these neurons. However, if the neuron has a higher cutoff, such as negative 0.6, then the image will not activate that neuron. So as a result, the images will only activate a set of neurons. Now, in order for reconstruction to be done, we actually have to do a subtraction then, since we're activating sets of neurons instead of single neurons. However, one important property that needs to hold true for this is that the weight and bias gradients of all neurons activated by the same image need to be the same. So if the first three neurons of the fully connected layer are activated by an image, the weight and bias gradients coming from this image for all three of these neurons needs to be the same. This is done through a second fully connected layer and modifying the parameters there, but the exact method isn't important in the context of Fed average. Rather, the property itself is important. And the reason that the property is important is because it's actually impossible to keep in Fed average. So what this means is that the method will have to have some modification. So because model parameters are changing after local iterations, it is impossible to essentially ensure that the weight and bias gradients will be the same. As a result, the way to fix this is through something called sparse activation. So images will only activate a single neuron instead of that set of neurons. The reconstruction equation will also become a bit simpler so that it's just a division instead of also including the subtraction inside. The way to do this is through something called a sparse activation. And this is done through essentially just a new activation function that has a double-sided threshold. So for instance, a ReLU activation function is only single-sided threshold, only has a single-sided threshold. On the other hand, this new double-sided threshold says that if the value is below a cutoff or above a cutoff, then it does not activate the image. And this essentially ensures that an image will only activate a single neuron. However, also recall that measuring the distribution of, for instance, the average pixel brightness is very important for efficient leakage. So in order for us to keep the same distribution and keep measuring that distribution, we actually have to scale the weight and biases to fit this. So the way we do this is we normalize the weight and biases by the biases of subsequent neurons. For instance, if the distance between two neurons biases is negative or is 0.1, then we divide the weight and the biases by this value. However, this does lead to a very large problem. So recall that activating multiple neurons is a bad thing. So if we have 64 images and we have 32 bins, then reconstruction of them would be very difficult as there are many images per bin. So the way to improve this is by simply increasing the number of bins. And when I say bins, it's the number of neurons. So let's say, for instance, you have a batch that is 64 and you have 128 neurons. Now, if there are two clients, you have a total of 128 images. So you double the number of bins to 256. And as the number of clients increases, you continue to increase this value. Now, herein lies the problem. As you increase the number of neurons, the number of bins, the distance between these subsequent neuron biases becomes smaller and smaller. With two clients, it's not a big deal, but as it go to 100 clients or even more potentially, this becomes very, very small. And now with the scaling of the weights and biases, these values actually become very, very large. And as these weights and biases get larger, the gradient magnitude really does not change too much. And as a result, adding very small gradients to a very large parameter results in floating point precision problems during reconstruction, because essentially we want to recover the gradients, but since they're so small compared to the gradients, a lot of the information is lost. And this is a very fundamental problem that prevents any sort of real scalability for linear layer leakage. If you look at the figure on the right, you can see that as the number of clients is increasing from 10 to 25 to 50, the reconstruction quality is also decreasing. Also keep in mind that these are the best 8 reconstructions out of all clients. The average reconstruction quality is going to be significantly worse than this. Now I'll introduce our attack Loki. And Loki really operates under a key insight that convolutional layers can be used to assist in linear layer leakage. And we do this through something called split scaling. Essentially, we can scale the number of convolutional kernels based on the number of clients. This removes the scaling of the fully connected layer, allowing the fully connected layer to stay fixed. Of course, the fully connected layer may need to change because of batch size, but the large scaling increase, which comes from the number of clients, is removed. And this also removes the scaling problem. Recall that as the number of fully connected neurons increases, that the weight and the biases scale up in parameter magnitude. However, if we fix the size of the fully connected layer, this does not need to increase anymore. So I'll talk briefly about how we do this. And we do this through something called an identity mapping set. Essentially, a convolutional layer can push images through the fully connected layer, or through to the fully connected layer. For a 3-channel image, such as an RGB image, you could think of using 3 kernels to do this. For instance, maybe the first kernel will push through only the red channel, and then the second kernel will push through the green channel, and then the third kernel will push through the blue channel. Now, the ultimate output of the convolutional layer then is the same image that came into it. Despite this, we can actually do multiple of these sets. For instance, let's say we have 30 kernels. We only need 3 for a single image, so we can actually have 10 different sets of these 3 kernels. And this leads us to being able to customize separate convolutional layer parameters for each client. So essentially a set of 3 for different clients. One thing that we do need to keep in mind, however, is that as the fully connected layer does not change in size and the number of biases does not change, this means that the bias gradients are actually aggregated across clients. So as a result, we cannot use these for the reconstruction anymore. And while this may be a problem, it is actually not a very large problem because the bias gradient is not actually required for reconstruction. If you look at the equation on the right, it looks very complicated, but what it's essentially doing is just setting the maximum of the absolute value of the weight gradient to be 1, essentially ensuring that this reconstructed image is in the range of 0 to 1. Now, sometimes the reconstruction will not be the exact same anymore. For instance, you can see on the figure to the bottom right that the reconstructed image is brighter than the ground truth. And this happens because the original image is not actually in the range of 0 to 1. For instance, maybe it's 0 to 0.7. Now, when we scale it so that the image is between 0 to 1, it appears brighter. Despite this, we can see that the image is still very visually distinguishable, and there are no problems there. For the final part of our attack, I'll introduce the convolutional scaling factor. Now, the convolutional scaling factor is a very simple but very powerful aspect of our attack. And essentially, what allows us to do this, or rather what is the insight behind doing this, is that larger gradients relative to the parameters is very desirable for a Fed average attack. Now, prior work thought that it was the opposite. They would think that smaller gradients relative to the parameters is good. And this is because if we have smaller gradients relative to the parameters, this is almost like the same as the Fed SGD attack. And the Fed SGD attack of linear layer leakage is actually quite easy and simple to do. However, what is interesting is that is not the case. Actually, staying away from the Fed SGD attack is much better for Fed average. And the reason why is because multiple image activations on the same neuron is bad. And we can essentially eliminate this altogether. For instance, let's say one image activates one neuron. Now, if a second image activates the same neuron, reconstruction ends up being failed. However, if the one image activates that neuron, and because the gradients are large enough that it pushes the parameters of the neuron away from the distribution, the second image can no longer activate that same neuron. In the previous case, no images are reconstructed because both images are overlapping. In the latter case, instead, we can reconstruct the first image. This leads to a higher leakage rate. Now, the way that we do this is through the convolutional scaling factor, essentially scaling the image up before going to the fully connected layer. So the fully connected layer weights multiplied by the inputs need to match the scale for the bias. If the image is, let's say, 50 times larger, then we'll have to scale down the parameters of the weights. So as a result, scale up the images with the convolutional layer, scale down the fully connected layer weights. And this is how we can have larger gradients relative to the weight parameter magnitude. Ultimately, the CSF allows us a couple things. One is we have a higher leakage rate, but not only is it higher, but it's actually more efficient. The second is that we have higher reconstruction quality. And this is because with larger values in the convolutional scaling factor, over local iterations, the convolutional kernels will still stay very similar to what they were before. If the value is small, the gradients will change the convolutional kernels so that the image that is propagated through the kernels will not be exactly the same anymore. Now I'll discuss some of the results for Loki. Loki has very high quality reconstructions despite a large number of clients. On the figure in the top, we see that with 100 clients in aggregation, this is a randomly sampled client, Loki has reconstructed the majority of images in all very high quality. Prior work, on the other hand, is barely able to reconstruct any images, and the one image that it reconstructs is, while somewhat identifiable, has lost nearly all of the details during the reconstruction. LOKI's scalability is very high. Regardless of the number of clients, there's no diminishing return on the leakage rate. We can maintain a very consistently high leakage rate. Prior work is really limited to attacking only a single client. For instance, robbing the Fed with model inconsistency, another work, allows it to attack a single client. So it is able to leak 50 images out of 6,400. On the other hand, LOKI is not restricted to attacking a single client. LOKI can attack all the clients and achieves 5,290 leaked images, which is nearly 83% compared to less than 1% of prior work. We'll look a little bit into the convolutional scaling factor for these experiments. Convolutional scaling factor really eliminates precision problems, but also stabilizes the convolutional kernel parameters. So what this results in is higher reconstruction quality. If you look at the figure on the right, we can see that as the CSF value increases, the SSIM score increases. Similarly speaking, the LPIP score is decreasing, where a higher SSIM is better and a lower LPIPs is also better. On the figure to the right, you can also see in the PSNR curve, another reconstruction method, the figure on the left, the PSNR is increasing, which is another reconstruction method where a higher value is better. So as the CSF value increases, the reconstruction quality is also increasing. What's also interesting is that the CSF results in a higher leakage rate. If you look at the figure on the left, you can notice that there's a very sharp jump at the beginning. And the reason this is the case is because initially with a very small CSF, the changes in the convolutional kernel parameters have rather a large impact on pushing the image through. However, as the CSF increases, it stabilizes this, and the image that is propagated through is still very similar to the original. So this leads to a very sharp growth at the beginning. However, the increase in leakage rate with a large CSF values is actually coming because images that activate neurons are pushing that same neuron away from the distribution. Now, images that would have activated it afterwards are no longer activating that neuron. As a result, we have a higher leakage rate with much higher CSF values too. This really brings us to the idea of efficiency. As the client batch size increases, the efficiency of prior work will actually decrease. Ultimately, as the batch size gets larger and larger, the linear layers will leak almost zero images. However, LOKI is the complete opposite. As the client batch size increases, the number of images LOKI leaks will keep increasing until it's nearly 1 image per bin. This would be almost perfect bin to leaked image efficiency. This is the case because increasing the CSF pushes these neurons away from the distribution. Therefore, the bin leaks an image, and then no other images can activate it. But also recall that this can only happen between separate local iterations. As the number of local iterations increases as a result, LOKI's leakage rate can also increase. To finish up the experiments, I'll discuss briefly these two. So LOKI can actually adjust the fully connected layer parameters to achieve higher leakage over several training rounds. Now, LOKI by itself does not require multiple training rounds, but multiple training rounds can make the attack stronger. The figure on the right also shows that LOKI adds only about half the model size overhead of prior work. And this is the case without sacrificing on any of the leakage rate. To close the talk, I'll give several takeaways. LOKI is a very powerful data reconstruction attack that allows scalability through convolutional layers and something called split scaling. Regardless of the number of clients, we can get very high leakage rate with very high quality reconstructions. Furthermore, the convolutional scaling factor, a very simple method of scaling the images before the fully connected layer, will enable even higher leakage rate, even better reconstructions, and ultimately very, very efficient leakage. As a final conclusion, private data can definitely still be leaked at a large scale, even in Fed average with secure aggregation. And this really points us to the idea that secure aggregation alone may not be enough. Really, defenses such as differential privacy, which are certifiable, or for instance, verification of the model are still necessary in order for federated learning to achieve the privacy-preserving property that is so necessary. Thank you, everyone, for listening to my talk today. That'll be all.